So given the wind stresses, we can obviously compute the Ekman velocity, Ekman vertical velocity. So here are our northeasterly and southeasterly and northeasterly trades meeting at the ITCZ with plenty of zonal winds on the equator. So remembering Ekman vertical velocity is curl tau over F, and F goes to 0 on the equator. We blank out the equatorial region, but we do have Ekman pumping, upwelling happening here because as the winds try to push the water here or drag them in this direction, they are pushed to the left in the southern hemisphere and pushed to the right in the northern hemisphere. So waters are diverging from the equator, like Moses parting the Red Sea, and you have cold, nutrient-rich waters coming up. So equatorial upwelling is a prominent feature in the eastern Pacific and the eastern Atlantic Oceans. Indian Ocean, because of the monsoon, is more complicated. But wherever you have a curl of wind stress that is negative, you have Ekman pumping, which means convergence. So these winds are dragging the ocean this way, Coriolis is pushing this way, ocean being dragged this way, Coriolis is pushing this way, so there is convergence in the middle, which means Ekman pumping. So that's a positive here. He makes Ekman pumping positive and Ekman suction negative. It's a sign convention, but honestly, if Z is upward, then that should be negative and this should be positive. Nonetheless, you have exactly what you expect. Here you have wind stress curl that's positive in the subpolar gyre, so you have upwelling. Same here, and the subtropical gyre have downwelling or convergence. The Southern Ocean is complicated. It's a channel, so it has currents, Ekman currents all the way. In fact, because there is no boundary, unlike here, winds can put more energy into the ocean. Ekman currents can go much deeper, sometimes all the way to the bottom, and so on and so forth. You can see coastal upwelling here. So winds blowing parallel to the coast can create Ekman transport offshore and create upwelling. You have wind curl driven situations here in the ITCZ. There is Somali upwelling here, offshore transport, but the wind stress curl here is positive, negative, so there is downwelling, and there is a different sign here with Ekman pumping happening because of the monsoonal winds, but these are annual means, so you have to be careful. You know that this completely reverses sign with the season. So coastal upwelling and various other situations are noted here. The confluence of the trade winds and the westerlies, equatorial upwelling here, blah blah blah. I shouldn't say blah 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 in a course. Just to remind ourselves again, we had Ekman layer, Ekman pumping into the interior ocean, and we had this situation of subtropical gyre creating a dome because of the convergence and pushing down of the isotherms. Just get an intuitive sense that if the pressure gradient has to go to 0 at some depth, then the isotherms that dip here have to be compensated by isotherms that dip up elsewhere, so you end up with this dipping up of the sea surface height. So convergence and downwelling give you high sea level and the doming of the surface. Upwelling and doming of the isopycnals will give you dipping of the surface and low sea level. So in the tropical Pacific, for example, there is low sea level here because there is strong wind-driven upwelling, Ekman divergence, and there is convergence and deeper thermocline here. So if you go from here to here, the sea level rises by about 50 centimeters, and there is doming in the middle of the gyre here. So if you go from the equator to the middle of the gyre, there is almost 2 meters of sea level rise, because sea levels are low here and high here in the middle of the gyre. So that's the ocean situation. Looking at the low latitude wind driven currents, this is just showing coastal upwelling. So if you have winds that are offshore, then that's going to drag waters off away from the coast, which means divergence. So there's going to be upwelling, and you are also going to set up a pressure gradient. So you're going to have geostrophic currents going south, and if you look at the vertical section, you can see that the winds are dragging water off and bringing cold water here, and if isopycnals dome up, sea level drops down, and there is a compensating pressure gradient in the interior. According to this book's convention, upwelling here, WE is greater than 0, which is actually opposite to what the other map said. Okay, and here winds are blowing into the coast, so there is convergence, downwelling, so the isopycnals are doming down and the sea level goes up, so the flow is actually going away from us. Here it's coming towards us, and then below the surface geostrophic currents are also going away from us. So you can see that there is wind driven currents and geostrophic currents that are in the same direction. This is how low latitude wind driven currents create the circulation. The other big things to look at, of course, the equatorial and extratropical circulations. In the equator, we talked about equatorial easterlies dragging water away from the eastern coasts. So you have the Ekman layer here and the Ekman divergence. So you have Ekman upwelling, and you have doming up of the isopycnals, doming down of the sea surface, whereas in the subtropical gyre you have doming up because of the trade winds and the westerlies creating the wind stress curl. Convergence, so you have convergence, so Ekman velocity upwards, Ekman velocity downwards, and doming down of the isopycnals, doming up of the surface. Okay, on the equator, that upwelling creates this kind of meridional circulation. So you have upwelling currents coming up, diverging at the surface, and sinking at some point and completing this cycle. He calls it meridional overturning circulation, which in fact in oceanography is reserved for the global thermohaline circulation kind of circulations. Type of circulations. This is just called the tropical cell, subtropical cell, depending on this is the equatorial cell, and then there is a broader subtropical cell that goes further out in the meridional direction. But you can again see the doming of the isotherms and isopycnals, and the sinking of the isotherms and isopycnals. Okay, we'll come back to this Sverdrup circulation in a minute. Leave this podcast here, but compared to the atmosphere, ocean circulation in the low latitudes is fairly straightforward. And we will see that ocean has a much more interesting role to play when we start talking about the monsoon and the El Nino and so on. Okay.